Okay, in this video I'm going to talk about the proctor compaction test, and I'm on the PolyLearn site now, and you can see we have a few things that are listed here. Report requirements, the data sheets. Here's a demonstration of the test and how it's performed, and it's a very common test, and it's used for grading control. When I say grading, I'm talking about preparing a site for a building that's going to be placed on that site. So preparing the ground, that's grading. So it could be changing the contours, changing the elevation by, adding earth or or cutting away earth or densifying the earth that's there. And that's what test has to do with, is densification. And, if you have loose material or soft material, of course, is pretty straightforward stuff. It's going to tend to compress when it's loaded, maybe even liquefy if it's sandy and wet. So densification is a very straightforward process to firm up that soil, and make it more suitable for building. Okay, so let's talk about the compaction test a little bit. So the whole point of this test, the proctor compaction test, is to create a relationship between the water content that the material is compacted at, and I'm calling that the molding water content. So the water content when you compact the material, and the dry unit weight that's achieved. Okay. So this is my symbol for unit weight, and we're talking about the dry unit weight. So I'm just going to emphasize that. And this is the water content during compaction. Okay, so for this test, Proctor developed this test, and it's been explained in class, I'm sure, so in the lecture, so I'll just do a little review. Soil's obtained from the field, and it's compacted into a mold with a hammer, and there's the number of drops and the number of lifts are all specified. And so what he's doing there is making a consistent or a constant compactive effort. So the compactive effort doesn't change for each of the trials that we do. So we have the same compactive effort. So that this is something you should know. Compactive effort, it's the energy delivered per volume. So energy over volume. That stays the same for each trial. So we put in the same effort. And let's say we have material that's, kind of dry, if you will. So it's at a kind of a drier water content. We compact it. We measure the dry unit weight. Well, we measure the total unit weight, and then we calculate the dry unit weight, and we can plot up one point here on the compaction curve. And then we take material, same material. We add water to it. We compact it again with the same compactive effort. It's got more water in it. The water provides some lubricating action. It compacts to a higher dry unit weight, and we get another point on the compaction curve. And that was a good thing, so we try to do that again. I mean, the whole idea behind this is to densify the soil, so we want to increase the unit weight as high as we can, or the dry unit weight. And we add more water, and we compact it again, and same energy, but we don't see an increase in dry unit weight this time. So what's happening there is, and you should read about this in Holtz and Kovacs, but what's happening there is that we have more water in the pores now, and so what before, when we were compacting and we were expelling the air, now we have water filling some of the pores that's incompressible, and so the water has a lower unit weight than the solid particles. So since the water is incompressible, we put in more effort, but we can't compact or densify the water, so we don't see an increase in dry unit weight even as we increase the water content. And if we do that again, we might get a point kind of down here. Of course, I've drawn this, like in an ideal fashion. but yeah, so this is the compaction curve. This is the Proctor compaction curve. And so the whole point of the test is to get this relationship between the molding water content, the dry unit weight, and then we can draw a smooth curve through the points. Okay, and then we can evaluate kind of the apex of this curve, and this is what we're interested in. So this value right here for water content, and this is what we call the optimum water content. So optimum, so that's where you get your kind of most efficient compaction. And then the top of the curve over here, this is what we call the laboratory maximum unit weight, dry unit weight. So this is the lab max dry. Okay, so yeah, this is why we run the test, is to assess this. Of course, it's the lab max, which means it's just associated with the level of the compactive effort that we put in. It doesn't mean it's the maximum we could possibly compact the material to. It's just with the level of effort specified by the test, or the compactive effort from the test, what is the maximum dry unit weight we're going to achieve? Okay, that's what it is. And what do we do with this? We use this to calculate, of course, relative compaction. What is relative compaction? Well, it's the dry unit weight in the field, and there's different ways to measure that. We're not going to get into that right now. So this is in the field. So when the contractor is densifying the soil to create a building pad, we have to check and make sure that they've densified it enough. The way we do that is to calculate relative compaction. So we have to measure the dry unit weight in the field. And then we need something to compare it to, and that's where this value comes in. This value comes in over here. So we compare it to the dry lab max, the lab and then we express this as a percentage, and that is the relative. So what's the compaction relative to the lab max, basically? So yeah, that's relative compaction. And of course, it's specified what the minimum relative compaction that's required for the project is specified in the specifications. And if they meet the requirement, great. They can kind of continue the work. If it doesn't meet the requirement, then they have to do something. Maybe the water content was too low, so they have to then rip up the lift, add water to it, and then get it closer to optimum, and then compact it. Maybe they'll get closer to the requirement. Okay, so that's the test. That's the compaction test. So these are the two important things to assess from it. Another thing we kind of look at is we usually draw on a saturation curve, and so that kind of ends up looking like this. Okay, so this is what we call the zero air voids curve. Zero air voids. So when I say zero air voids, that means it's going to be 100% saturated, right? Because if there's no air in the voids, it's all water. So this is associated with 100% saturation. And to calculate that curve, we could compute water contents that are associated with 100% saturation and the corresponding dry unit weights. We would, of course, have to make an assumption or measure the specific gravity of the solids. So for our test, we're going to assume specific gravity. I'm going to call that G sub s. That's specific gravity. We're going to say that's 2.72. Okay, so why do we put this zero air voids curve on here? Well, one thing you couldn't have it. It's kind of a boundary for possible data points. So that it would be impossible to have a data point on the other side of the zero air voids curve. So that's one reason. That's probably the chief reason why you'd have the zero air voids curve is you know that data has to be on the left side of the curve because you couldn't have a value that was over here. So that's zero air voids. We can also plot up different saturation curves. So we could plot saturation curves of like 80% saturation, 60% saturation, and so on. And again, all we'd have to do is come up with a relationship between the water content and the dry unit weight, the saturation level, and the specific gravity, calculate some data points, make a curve. Okay, so that's something that you're going to do for this activity. So equations are really straightforward. We're talking about unit weight. This could be this could be density also, or it could be unit weight. They're both used, easy to transfer between the two. But for the test, we have a mold of known volume. So the volume of the mold that we compact the material into, so this is the volume of the mold, it's just a cylindrical mold. You'll see it of course, in the video, the demonstration video. This is known. It happens to be 1/30th of a cubic foot. And so we're going to compact the material in that mold, and we're going to measure the weight of the material in the mold, or we're going to measure the mass of the material, and then we're going to calculate the total unit weight. Or it could be the total density. It doesn't, either one. Let's say we're working in terms of density, then that's going to be the mass over the volume, right? The total mass over the volume, which of course is the volume of the mold. And that's known. Okay. And after we compact the material and get the total unit weight, then we extrude all the material, we take it out of the mold, and then we take a portion of it to measure the water content. So we measure what the water content, what it was during compaction, or the molding water content. And then if we have the water content and the total unit weight, then we can, or the total density, then we can calculate the dry unit weight, or dry density. And this is a helpful equation. I'm sure you used it many times when you're doing the phase relation problems. So we're talking about the total, take the total and divide it by 1 plus the water content. And that is the dry. And of course this has to be in a decimal, the water content, for this equation. Okay, so you have the, so then when we've calculated these things, we have the dry, either we could do this in terms of unit weight or density, but we have the dry, we have measured, this is measured with the oven. So we have the water content, the dry unit weight. Well, yeah, of course, that's what we need to plot up all these values. We can make the compaction curve. Okay, so basically the equations that you're going to use are over here. And let me make one other thing clear. So this is relative compaction. There's another term that kind of sounds like that, but it's different. It's called relative density. So it usually there's different symbols, but a common one is d sub r. Relative density, so this is relative density, d sub r. It's not the same as relative compaction. It's different. And I'm not going to go through though. I'm not going to talk about it in too much detail, but relative density is associated with clean sands and gravels. And it's comparing the void ratio of the material to a minimum and maximum void ratio. And so it's different than relative compaction. And you guys have probably reviewed that in lecture, so I just want to make sure that's something that's clear. Okay, so that's a little bit of background about the test, and of course watch the video demonstration, and I think some of my notes will be more clear. Now let's look at what we have on PolyLearn here. Okay, let's go to the data sheets. Okay, so I've taken some data from an old class from a previous section and provided it here, and what we have are 4 data sheets with each has a trial. Each data sheet has 3 trials. So we have the 12 points, and so what we're going to do is create one compaction curve with the data sheets, all the data from this class. So we're going to use, I'm going to just scroll down. So we have all these data sheets. You're going to use all the data sheets to create the compaction curve. So you have all those points. So on your curve, instead of just like I drew this, just showing the 4 points, you're going to have all 12 points. And it was the first time we were running, for what this is previous data from a previous section. So it's the first time they're running the test. So there's little errors that are going to occur as far as, getting uniform lift thickness, uniform compaction, trimming the ends of the sample to fit the mold exactly so we can measure the mass per the volume that we're using. So there's definitely little errors that occur. So I've drawn this, all the data points are picture perfect on our idealized compaction curve. We're going to not have that, so we're going to have 12 points on here first of all, and maybe a couple of them might not fit in with a curve that you draw in. Nevertheless, you might have to use a little judgment to possibly when you construct this curve. And let's have a look at Holston, Kovacs, and Sheehan and just look at some typical curves. So I'm going to Holston, Kovacs here, and Sheehan. We're looking at figure 5.4, and they have some typical curves for different soil types. So the shapes of the curves are provided here. Of course, I didn't mention this, but we're using the same soil that we've been using all quarter. So you know what the soil is. It's clay sand, number 3 on this one. So here's a typical shape for a clay sand. So the reason I directed your attention to this figure is that when you're fitting your data, you can be aware of what the shape of this kind of curve looks like, and it might be helpful to do that curve fit because some of the data points might be a little bit wonky, if you will, and we might have to kind of potentially, our curve likely won't be able to go through all the data points. Well, we want to go through the majority of them, but if we have one that doesn't fit in with the others, then we don't want to use it. But one thing to point out is we are looking for the maximum. So if we do have a data point that's up, up to the peak up here somewhere, we shouldn't draw our curve and not have it go through the maximum, because that's the whole point of this. Unless we had maybe a drop off over here and then we had a data point that was like way up here or something that's clearly wrong. But if you have a data point that's near optimum water content, and it's up here higher, we should have our curve go up and get that data point. Okay, so yeah, different shapes of the curve. It's not a parabola. The soil type kind of indicates the shape of the curve. There's a lot to talk about with the shapes of these curves and whether the material is moisture sensitive or not, but that's kind of beyond what we're going to cover in the lab. But be aware of this figure. And this chapter, of course, you're going to want to review this chapter, and it's going to be helpful to create this report. So have a look at this chapter in detail. Okay, so let's go back to the data. You're going to use all the data, and this is just one of the data sheets here. There's some extra scribbles on these. These are just, data sheets from students, so just ignore all that stuff. The important thing, we have two parts of the data sheet. This first portion up here is used to calculate, in this one in terms of density, it's used to calculate the total density, and then the bottom part is used to calculate the water content. Okay, so we have the mass of the mold that was used when we compacted the material. And if you look, when you watch the video, you'll see what the mold looks like. It's just a cylindrical mold. The masses of each of the molds is a little bit different. So this is 2,000 grams. Let me just kind of scroll down to another data sheet just to point that out. This one's 2,002 grams. Okay, so you have to use the mass of the mold, obviously, that's associated with the data that you're looking at. The volume, we're going with a nominal volume. So I said before, it's a 30th of a cubic foot. Everything's in centimeters cubed here. Is this the correct conversion? I didn't do it. So, make sure you do this for yourself. This is, and confirm that that's correct. Okay, so what do we have over here? We have these three trials. And first of all, we have the mass of the mold with the wet soil. When it says wet soil, that just means it's at whatever water content that the material was conditioned to before starting the test. So the mass of the mold with the soil in it, okay? So then if we subtract out from this value the mass of the mold, then we have the weight of the soil, and we would know, or this is in terms of mass, then we have the mass of the soil. So this is the mass of the soil that fills the volume over here, and then we can compute the total unit weight or the total density, and that's what's done down here. Okay, so we have that. And written in here it says W target 8, 12, 17. So what that means is when we did this activity, each group was given 3 different target water contents. So they were trying to get close to 8, trying to get close to 12, trying to get close to 17. But what the actual water content was, we measured it, and that happened in this section down here. So of course, to measure the water content, it's just the mass of the water over the mass of the solids. So let's have a look here. We have some material we're going to put in a bowl. First we weigh the bowl, then we take some of that soil that after we've compacted it, and it's wet or moist, we place that in the bowl, we get the mass, then we take that out of the oven, and then we put it in the oven, evaporate all the water, weigh up this soil again in the bowl, and then we have the dry mass. So for how much water was in the soil, well, we just take the difference of these two, right? That's the mass of the water. What's the mass of the solids? M sub S is solids. Always remember that. That can be confusing. It's not soil, it's solids. How do we get the mass of the solids? Well, if we take the dry mass of the soil plus the bowl, subtract out the mass of the bowl, then we have the mass of the solids, and then we can compute the water content. Once we have the water content and we have the total density, then we can compute the dry density down here, and then you can convert that to a dry unit weight. Okay, so that's all we're doing. You're going to use all the data from each of these data sheets to create the compaction curve. Now let's have a look at the report requirements. So it's going to be an individual letter format report. This is the format, brief introduction, mention the test method. We're doing the standard test. So there's 2 tests. There's 2 proctor compaction tests. One's called the standard effort, one's the modified effort. We're doing the standard effort, and so that's ASTM D698. And on PolyLearn, the test method's provided there. So refer to the test method. Same old stuff here. What do you need to put in the summary of findings? Provide the compaction curve that I've been talking about. We're going to use SI units. This is a figure that we already looked at in Holtz and Kovacs and Sheehan. And be careful how you construct that figure. It's not going to be a parabola. You saw the different shapes. Make sure you label the dry lab max and the water content, the optimum water content. Include saturation curves, 60, 80, and 100%. So here's 80. The 100% curve we call the zero air voids curve. So you're going to have this 100%. You're going to have the 80% saturation curve. You're going to have the 60% saturation curve. And make sure those are all labeled and easy to read. So this could be a curve associated with a 60% saturation. This could be the curve associated with 80% saturation. Okay, so that's what that means. Calculate the use specific gravity of 2.72. Okay. Calculate degree of saturation for the peak of the compaction curve. All right. Does it fall between, this is kind of a typical range. It doesn't have to be exactly in this range, but maybe close to it. And then have a look at chapter 5 from Holtz, Kovacs, and Sheehan as well. So, calculate whatever you choose for the maximum. So whatever this point is, use your dry lab max and your water content, calculate the degree of saturation. I just kind of hastily drew this 60% in. It's likely your result, this 60% curve is likely going to be kind of over here more, because typically you fall in with about 75% or so saturation at your lab max. So here. Slightly better. Okay, so you calculate saturation at the lab max. And what else are you going to include? Let's see. Just explain why we have an initially from dry material, and when we compact it we have an increase, and then essentially we get a decrease. Make sure you read the book and cite the textbook. And then also, what type of equipment would be most appropriate for compacting this type of soil? We all know it's a clay sand, and it has like 40% clay. So you'll read about the different types of compaction equipment and how they work and how they're suited to different types of material. But note, when you have 40% clay or fine grained material in the sand, it basically is going to behave a lot more like a clay than a sand. So even though it's technically a sand because it's clay sand, this is not a clean sand, and you're not going to use the same type of equipment that you would use on clean sand. So this is going to behave a lot more like a clay than a sand, even though technically it is a sand. So be aware of that when you answer this question. Okay, let's see. And then just the typical stuff. That's it. Down here, I think that covers it pretty well. I'm going to just say one other thing about the proctor compaction test, which is Proctor's 4 points of compaction. So if you remember nothing else from this lab, remember Proctor's 4 points of compaction. So the one is in no particular order, the soil type. Every soil type is going to have a different characteristics, different lab max. So soil type. Number 2, compactive effort. So how do we achieve the relative compaction? We may have to put in more effort for the particular soil type, but compactive effort. Number 3, dry unit weight. What is the dry unit weight we're going to achieve? And number 4, you guessed it, water content. And of course, let's just make this very clear. When we're talking about water content, it's the water content during compaction, right? So what is the water content when we're compacting the material? Later, after it's compacted, it could dry out, the material could dry out, or it could rain and it can get wetted. But the relationship that we're trying to assess is the water content during compaction and the dry unit weight that's achieved. Not what's the water content later. We don't care about that. That's something that can change. We're just talking about the water content during compaction. So those are Proctor's 4 points of compaction. I'm going to just write during compaction just to make sure this is emphasized. And I'm calling that the molding water content, like when the soil's molded. And that's the reason, since the water content could change later, that's the reason when we're calculating relative compaction, we're looking at dry unit weight values and not total. Because the dry value is not influenced, it correlates directly to the void ratio, which the whole point of compaction is to reduce the void ratio and bring the particles in closer contact. So if we were looking at total unit weights here, that would vary depending on the water content, right? Once we calculate the dry unit weight, that's not something that's going to change if the water content changes. Okay, so dry unit weight correlates directly to void ratio. The whole point of this is to reduce the void ratio. That's why we have to compare dry to dry. If we were comparing wet unit weight or total unit weight, that would vary with water content changes. And so, for example, let's just say we weren't doing it like this and we're comparing total unit weights, and let's say we compacted the lift in the field and we didn't have the specified relative compaction. And so what we could do then, hypothetically, is then we just add water to the site, right? And we allow the pores to fill up with water. Well, what have we done? That if we did this activity that I'm describing, then we've just increased the total unit weight, right? Because now we have water in the voids. But we didn't do anything for compaction. We still have the same void ratio. All we did was put some water in the voids. Okay? Well, that didn't help reduce compressibility. So that's the reason why we don't compare wet to wet, we compare dry to dry. Okay, so yep, Proctor's 4 points of compaction, and I think that'll do it for this video. Have a good week. All right, signing out.